Engineers had done this 11 times before without incident, but this time was different. As the structure passed 65 meters in depth, witnesses heard a low rumble, then a bang, then the unmistakable sound of water rushing in. Within minutes, the platform known as Sleipner A was sinking, a meter every 60 seconds, until it vanished beneath the surface of Gansfjorden entirely. The collapse registered as a magnitude 3 earthquake. No one was killed, but the cause, when investigators finally found it, was almost impossible to believe. It wasn't a storm, it wasn't bad luck. It was a tiny, repeated error inside a piece of engineering software. A miscalculation that had gone unnoticed through years of design and months of construction. To understand how this happened, you have to go back further to the 1970s, when Norway discovered it was sitting on one of the richest oil and gas reserves in the world. The North Sea was brutal water, deep, cold, and battered by constant storms, and getting oil out of it meant building platforms unlike anything that had come before. Steel structures worked, but a Norwegian company called Norwegian Contractors had pioneered something different, a design called Condeep, short for concrete deep water structure. Instead of steel legs, a Condeep platform sat on an enormous concrete base, a honeycomb of individual cells that acted like a foundation and a flotation system at the same time. You could tow the whole base out to sea, fill the cells with water to sink it gently to the seabed, and build the working platform on top. By the time Sleipner A came along, this method had been used successfully 11 times. It was considered safe, proven, almost routine. Sleipner A's base structure was a monster of engineering. 24 cells arranged in a cluster, with 4 of them stretching upward to form tall shafts that would eventually support the platform deck above the waves. Building it took nearly 3 years. Thousands of tons of concrete were poured and reinforced with steel, layer upon layer, in a process as much like sculpture as construction. And before any of that concrete was poured, the entire structure had to be designed on paper, or rather on a computer. Engineers used a finite element analysis program called NASTRAN to simulate how the structure would behave under the immense pressure of deep water. The software broke the platform down into thousands of tiny mathematical elements, calculating the stress on each one, then adding them together to predict whether the walls would hold. It was the same approach that had worked on every previous Condeep platform. On August 23, 1991, the final structure was towed into Gansfjorden, outside the city of Stavanger, for what should have been a routine test. The plan was to lower the base slowly, about 1 meter every 20 minutes, using a controlled system of ballast tanks, until it reached the depth needed to attach the deck. Workers monitored the process closely. Everything seemed normal as the structure descended past 40 meters, then 50. But deep inside the base, in a section called the Tricell, where 3 of the buoyancy cells met at a junction of concrete walls, something was quietly approaching its breaking point. As the platform reached around 65 meters down, the water pressure pushing against those walls finally exceeded what they could withstand. A wall cracked, then another. Seawater began pouring into the structure faster than the emergency pumps could remove it. Within moments, the calm test became a crisis. The sound of rushing water filled the shaft. The platform, which moments earlier had been descending in a smooth, controlled motion, began sinking on its own, dropping at roughly 1 meter per minute, completely beyond anyone's ability to stop it. As it sank deeper into the 200-meter fjord, the remaining buoyancy chambers, still sealed and full of air, began to implode under the crushing pressure, one after another, like a string of explosions. The shock waves were powerful enough to register on seismographs as a small earthquake. When it was over, a structure that had taken 3 years and roughly $200 million to build was a pile of rubble on the floor of the fjord. In the days that followed, Statoil, the state oil company overseeing the project, launched an investigation, bringing in structural engineers and researchers from SINTEF.
This is the critical junction. The displacement readings are accelerating. We must re-examine the finite element analysis on section 4B. The stress load is too high.
One of Europe's leading independent research organizations. They had 24 other possible explanations to rule out before they could trust their conclusion. Was it a flaw in the concrete mix? Was it a construction error? Was it something about how the structure had been towed? One by one, these were eliminated. The investigators kept coming back to the Tricell, the same cluster of walls where the first crack had appeared, and to the calculations that had supposedly proven those walls were strong enough. What they found was unsettling in its simplicity. The finite element model used to design those walls had divided the structure into roughly 23,000 individual elements for analysis. But in simplifying the complex three-dimensional geometry of the Tricell into a model the computer could process, the engineers had introduced a small, systematic error in how shear forces were distributed across the simulated elements. The result was that the software underestimated the actual stress on those walls by around 47%. In practical terms, the walls had been built to handle less than half the force they would eventually face at full operating depth. Nobody had caught the mistake, because nobody had cross-checked the computer's results against simpler, traditional hand calculations, the kind of mathematics that engineers had relied on for generations before computers existed. The software was new, fast, and trusted, and that trust in this one critical section of the design had not been verified. It is worth pausing here on what this really means, because it is easy to hear 47% and assume it was an obvious, careless mistake. It wasn't. The error was buried inside thousands of pages of calculations, hidden in the way one complex three-dimensional shape had been translated into a simplified computer model. Later analysis showed that if the error had been caught, a more accurate model would have predicted failure at a water depth of around 62 meters, remarkably close to the 65 meters at which the real structure actually failed. The mathematics, in other words, was consistent. It was simply wrong from the very beginning, in a way that nobody thought to question. According to widely repeated accounts, when the project leaders were called before Statoil's board after the disaster, they expected to be fired, or worse, to see the entire Condeep program canceled. Instead, the company's director reportedly asked them a single question.
Can you build a new one before schedule?
The team went back to work, redesigned the failed sections with the error corrected, added additional reinforcement where the original calculations had been too optimistic, and rebuilt the entire structure from scratch. The new platform was completed in June 1993, ahead of schedule, this time checked using both computer modeling and traditional manual calculations as a safeguard against exactly the kind of blind spot that had caused the first failure. Sleipner A still stands today, producing gas in the North Sea, supplying energy across Europe, decades after the wreckage of its predecessor settled onto the floor of a Norwegian fjord. But the cost of that single hidden error in money, in time, and in the confidence of an entire industry became one of the most expensive lessons in the history of modern engineering. A reminder that even the most advanced technology still depends, in the end, on someone willing to check its work. It takes you 2 seconds, but it helps us bring more of these incredible engineering mysteries to life. If you found this breakdown fascinating, drop a like and subscribe right now. Turn on notifications so you don't miss the next disaster analysis. Thanks for watching. See you in the next one.